So we know the solution of Schrödinger's equation gives the allowed states of an electron in an atom. The electron is described by a wave function psi, which contains all the information about its quantum state. The wave function itself has no direct physical meaning, but the square of its magnitude, psi squared, represents the probability density of finding the electron at a particular point in space. This means Schrödinger's atomic model is inherently probabilistic. Instead of predicting an exact path, it predicts regions where the electron is most likely to be found. This model explained almost all experimental observations in atomic spectroscopy. The first was the observation of quantized energy levels, seen as discrete spectral lines. When Schrödinger's equation is solved for an electron bound to a nucleus, only certain solutions are allowed, each labeled by the principal quantum number n, which fixes the energy of the electron. Since electrons are bound in 3 dimensions, solving the equation fully introduces more quantum numbers. The azimuthal quantum number L arises from the angular part of the wave function and determines the orbital angular momentum and shape of the electron cloud. The magnetic quantum number m describes the orientation of this angular momentum in space and becomes observable only when an external magnetic field is applied, as seen in the Zeeman effect. However, spectroscopy revealed an additional splitting of spectral lines even without a magnetic field, called fine structure. This led to the discovery that the electron has an intrinsic angular momentum called spin, represented by a 4th quantum number. The interaction between spin and orbital angular momentum explains fine structure and magnetic behavior, confirmed by experiments like Stern-Gerlach. Thus, a complete quantum description of an electron requires 4 quantum numbers, and Schrödinger's model replaces fixed orbits with a probabilistic wave picture of the atom.